Welcome back to ECE 442-542 for the final time, other than the review session. There is a final exam review session that I've scheduled, but we don't have to have it if no one wants to show up. It's scheduled right now at 4:30 tomorrow, reading day, in Harville, room 204. Does anyone want to have that review session? Okay, boy, almost a majority of the class. That's not saying much based on the attendance, huh? But for those of you listening, there will be a review session. I'll try to remember to email that out after class. Your project, if you haven't already submitted, is due today. And there is an additional lecture. I think this is lecture 8.4 that I'm doing now. 8.3 is a supplement, and it gives you an example of working through the state space design approach, and there's some MATLAB included if you want. There will be probably half of the final exam will be MATLAB. Just wanting to see if you're paying attention. Just checking. There won't be any explicit MATLAB on there. You won't be having computer access. So if you start answering with MATLAB material, I will start to be suspicious when I'm grading the final exam. But the final exam is Thursday, a week from tomorrow, and it is at 1 o'clock in this room. This room is Giddings 201. Well, a lot of us don't pay attention to what room it is. We just go to the same spot. If you want to have questions considered, I'm not going to guarantee answers, but we will have additional office hours starting tomorrow since it's reading day, but that's the normal Thursday office hour. But then we'll have them every day of the week up until the final, except on Saturday and Sunday. I'll give you those days off. Okay? I'll be grading projects or something, I'm sure. All right, those are the times and those are actually 2-hour time slots. Other than the very last one, I want you to make sure and get a balanced meal in before our final exam, which is, what did I just say? 1 o'clock on Thursday, the last day of finals. Here are our goals for today, and we don't have very many. Again, that was a little bit of a joke, but a lot of this is telling you where you can take the material that you've now learned this semester. Where can you go from here? And it's based on right now Unit 8, which is the state space design. But first we'll talk a little bit about the final exam. Then we'll go through A through F different block diagrams. And each of those A through Fs represent a different strategy in terms of control. You will be responsible for A, B, and C in this class. The others are for your enjoyment. But we will look at A, B, and C, and then what I want you to be able to do after this class is be able to work with D, E, and F, or know how to use those, and also to start being able to do integral control. And we'll walk through how you can derive that particular state space representation in what we will call augmented system matrices, and that's useful in approaches E and F as well. But in E and F, although we're saying full state, now we're assuming that we create or we build structures that allow us to estimate the full state, and in E, that's all we're doing. In F, we're actually using that full state estimator in our feedback control equation, or as our input into the system. Then we'll look at a challenging system to control. By that I mean it now has poles outside the unit circle, zeros outside the unit circle, and if I gave that to you on the final, you might start throwing things at me. Because you might go, well, he gave us a couple of ways of maybe approaching this, but I can't see how it works. Well, that's why we're doing E and F, so that in the future you can say, oh, let me try this, and that might give me a clue as to how to design poles and zeros to put onto my Z-plane to actually stabilize this challenging system. I don't think we will get there, but this is how we could proceed if we had unlimited time. I know you probably have nothing planned for later this evening. Probably no manicure or anything like that. Not yet. That's maybe after all your exams, before the convocation. But full state estimators, how do you develop those equations? And you should be able to develop those based on the block diagrams that I give you earlier. And a full order compensator, how do we now find that from this full order estimator with the controller incorporated? That's possible to you after tonight, is what I'm hoping. Final exam is comprehensive, and there will be 15 questions distributed across the entire semester. But in this class, a lot of the later material actually depends on the early material. So if you can do you better be able to do the later material, and that might help you do or remember how to do the earlier material in the class. Bring a photo ID. That worked pretty well last time. I want to keep doing that to the exam. You'll have 4 sheets of notes, and you can also bring in a Laplace transform table and a Z-transform table. You might want to bring in a protractor, a straight edge, maybe not a compass, but you might if you want to really get neat with your sketches. And you can have a calculator, but that's plenty to try to keep track of. Those notes and equipment to draw with, something to write with, and a calculator. That should be consistent with what we've had all semester. Let's get into these A through F's, block diagrams, and equations for some of these block diagrams. Here's a state space representation, and I'm just saying it's an A state space. It's not the state space, because state space representations are not unique. We could have 80 different state space representations, and they could all be modeling the same system. We're assuming we have Nevada state variable components, or the X vector is now N tall. The input could be M, or Michigan tall, and the output vector Y could be Q tall. And here is how you could now describe those equations, the dynamic equations, which are the first equation, and the algebraic equation, which is the output equation, in a block diagram description. And obviously that delay is a block of delays, because your state vector X is Nevada tall, or N state variable components in your X vector. U and Y could also be vectors. They don't have to be single input, single output, and that's the power behind a state space representation. You can easily, well, I maybe shouldn't say easily, but you can extend a lot of these ideas and concepts to multi-input, multi-output systems much more easily than if you start in a transfer function domain or setting and say, okay, now I have 3 inputs and 4 outputs. I don't know what I do. Here, you just build the gamma and the H matrix to incorporate those multiple inputs and multiple outputs. You can then use that algebraic or dynamic equation, z-transform it, and derive the transfer function in terms of the state space representation. And that's now H, whoa. Wow, falling asleep here. Is everything else okay? So it's H times the quantity Zi minus phi inverse, the input matrix gamma, plus J. That's G of Z in terms of these state space matrices. And that G of Z is an open loop system. If we now wanted to apply full state feedback in this state space setting, we can. And what does this do? This tells our system how to behave. The K matrix. That now allows us to change the dynamics that exist in our system. And what influences the dynamics in this system? Let's say that the red material is not yet on there and we're still back in representation A. How do you tell me any information about the dynamics of that system? What would you look at or say, oh, this is what I need to find or compute? Pardon? Did I hear anybody? I thought I heard somebody. Okay, eigenvalues of phi. So eigenvalues of phi give us the poles of this system. And if somebody said, how's this system going to behave in the open loop if that red piece wasn't there, you could say, oh, I can tell you by looking at the modes, which are the eigenvalues of the system matrix phi. We may not be happy with those modes. And that's why we introduce this K, this full state feedback gain matrix. We're assuming we can go in and access the full state vector X. We're not picking off Y, the output. Now we're saying we're going into the system more internal and saying, oh, let's grab the full state vector X, scale that, each of those components according to how the full state feedback gain matrix K is created, and using that to drive or influence our system dynamics. And now we're changing the system through the insertion of that full state feedback gain matrix K, and if the system is controllable, then we can do anything we want with those closed loop eigenvalues. We can put them anywhere we want inside the unit circle, I'm assuming, since that would keep our system stable. But you could put those closed loop eigenvalues or the closed loop poles anywhere if your system is controllable. And you should know how to derive the controllability matrix or answer that question on the final. Is this system controllable? That now you create this controllability matrix, which is gamma, then you pad on another set of columns, which is phi gamma, then you add another set, which is phi squared gamma, and you just keep going up to phi raised to the n minus 1 power times gamma. That B representation told the system how to behave, but it really didn't give us any flexibility on telling it, I want to command this system to go to a certain value or location. I want it to go to 4 when I give it a reference input of 4. The last one didn't have this additional piece, this n sub 1 R of L making up U of L. U of L was just minus K X of L in the regulator problem. Now we can track. Now we can follow or track R of L because we now allow the injection of a reference input. That now allows us to select n sub 1, and you might look at the example in the lecture, the supplemental lecture, lecture 8.3, to see how you can use n sub 1 to allow you to actually track a constant input. If I say go to 2, it will now go to 2. Whereas if N1 was just an arbitrary constant, you might go to 0.04. And that might give you a big steady state error that you don't want when you were looking to go to 2. You can do what we had done before in terms of finding the closed loop transfer function by first substituting U of L or replacing it with this full state feedback reference input expression that's in red. Put all of the terms together that are common or combine the X of L terms. That gives us now a new phi, which we will call phi sub c. That's our closed loop system matrix. That's made up of phi minus gamma k, and that's how we want our system to behave. How would you locate the eigenvalues in phi sub c, or what would guide your selection of the eigenvalues of phi sub c? Closed loop poles. How do you select closed loop poles? You pull out your breakfast cereal box that has circles and hearts and wedges in it. Remember? That's your performance criteria. Your settling time, your percent overshoot, your peak time, that's what guides your concept or your thinking on where do I want my closed loop poles to be located. So you pull out your box that has hearts, and in terms of hearts, which heart is where? Well, that's a crazy question, but we have hearts that range from zeta equals 0 up to zeta equal 1. Zeta equals 0 is what shape of a heart? What did I say, zeta equals 0? What's the shape of the heart when zeta is equal to 0? Zeta equals 0. Zeta is our damping ratio, and if our damping ratio is 0, that seems to say we don't have any damping. So it's the unit circle, isn't it? So our heart now is this unit circle with zeta equal to 0. As we increase zeta, we're approaching really the real line. When zeta is equal to 1, we're between 0 and 1 on the real axis. And we collapse that heart down to a flat, so now you flatlined, which that's not really how you interpret zeta equal to 1, because zeta equal 1 is good, probably. That is like critically damped in terms of your system behavior. But in between that, with zeta equal to 0, you have no damping, and with zeta equal to 1, you're critically damped or over damped, depending on where you are on the real line with multiple eigenvalues. Here's your closed loop transfer function with a non-zero reference input. What has happened? Now we have the transfer function between a reference input R and the output Y. And we now have that one new term appearing in this transfer function, t sub c of z, and that one new term is capital N sub 1. That's this matrix that we're using to inject this reference input signal or information into our system. That we haven't yet determined how to pick that. How do we design N sub 1? Well, I'm going to tell you. Since you're listening quite well, I feel like I'm having a reading activity or something. Everybody's enjoying their snacks while I'm reading to you, so that's good. Man, I'm getting hungry. What time is it? About 2 more hours and I can eat. Oh yeah, we'll get out the French bread maybe later when we start drawing root loci. We want to pick N1. Got distracted. It's easily distraction day, but we're selecting n sub 1 to create a DC gain of 1 if we want. Or I might ask you to give me a DC gain of 1/2 or 2. And you would use that information to determine what you want for your n sub 1 matrix, which if it's single input, single output, little n, so if it's single input, n sub 1 is a 1-by-1 matrix, or it's scalar. If we have single input, single output, that makes this expression, which is h times I. Where did the z go? That was a question. So z went to 1, so I didn't include it because I'm looking at the DC gain. I'm setting z equal to 1. But I minus phi sub c, if our system was 10th order, that's a 10-by-10 matrix that we invert. But when we pre-multiply by the output matrix H and the input matrix gamma, if it's single input, single output, all of that collapses down to a scalar. That's just going to be a number. We're dividing 1 by that number, and that will actually give us this numerical value for n sub 1, which was a 1-by-1 matrix or a scalar. The problem with this, if you're building something, if you finish this class and you go, oh, I need to tell the system where to go. Tharp told me how to do that. I built an N1. Ugh. And then you start simulating it and you go, well, I told it to go to 2 and it went to 1.8. What? Was somebody storing to me? Yeah, it's story time, like I said, but it depends very much so on the matrices that you're using for your state space representation. And if they're off, if they're uncertain a little bit, your N1 is not going to give you a perfect scaling between your reference input and where you want to go with your output Y. This approach is susceptible to parameters not being completely known in your system matrix phi, in your input matrix gamma, and in your output matrix H, because they're all in that denominator expression. And if you have variability, I think some people are doing their project on variability of parameters. Maybe you finished your project. Still have a few hours. I'm surprised you're in class if you're stressing about the project, but I'm looking forward to reading all, however many, 70, whatever number of projects I need to read. Anyway, part D, full state feedback with integral control. And this is actually going to help overcome that susceptibility problem I just referred to in C. Remember when we applied integrators in our transfer function based design? As long as we kept our closed loop system stable, that integrator was very helpful in giving us zero error to constant inputs. We could track any constant input that we wanted as long as we had the system closed loop stable. And that is what this approach is going to allow us to do. We will be able to, if we can stabilize the closed loop system, we will be able to inject a 4 and get out a 4. By what? By somehow introducing integral control. And if our system is single input, single output, we really only have to add in one integrator. We don't have to add in 10 if our system is 10th order. No, we just have to add in 1. And that's what we're going to now see in the block diagram for D. This should look somewhat familiar if you, maybe I should have done all of that integrator piece in red. I think I should have, but I'm not now. But the blue piece and the black piece on the right look very similar, don't they? Other than now I've changed the K because I now have two different parts to my K. By that I mean here is a new component of my state variable, and there's my previous state variable, so that now my full state feedback gain matrix is going to include, it's going to be augmented. One is going to be the same dimension as our full state feedback gain matrix, which is now what we're calling k hat, and the other one is this k sub I. And we've introduced now some new dynamics into this system, which is this integrator block. And what's that integrator block doing? It's now looking at the comparison between our reference signal R and the output Y. Y's on the right somewhere. Well, it's nowhere. It's supposed to be right there. So I highlighted it. There's Y. We're comparing Y and R. That's now our air signal. Here's our air signal E. We integrate that air and scale that integrated air with k sub I and use that in combination with the full state feedback minus k hat x to drive our system. If we can now stabilize the system by the selection of k sub I and k hat, then we can track signals without any error. Question? So now I have so the question was, I have an extra state. Yes, so now the United States has 51 states. No, the block diagram has an extra state. We still have 50 states, don't we? Anyway. Yes, we have an additional state. We've introduced one more Z, or one more pole, in our system, and so we have augmented our system. This is what I'm going to say. We've augmented our state space representation. Originally, that z to the minus 1, that's a bank of z to the minus 1s. Phi is still 10 by 10, possibly. So maybe we had a 10th order system. Now we've augmented it. We would now have an 11-dimensional augmented state vector. The first 10 will be the original 10, and that 11th component will be this x sub I. That's what we're doing here with this integral control. Once we have those, we will use all of that information in our control signal. U of L is now minus k hat x of L minus k sub I x sub I. Two more. This one is now our full order estimator. This one is saying, oh, can you actually estimate x if we can't go in and access x? If our system now is, let's say, some rocket engine, or we're trying to control this very dangerous system in terms of sensors, maybe we can't sense all of our state variable components. So we can't go in and internally access x, little x of L. But maybe there are some censored variables through the output y that we can measure, and we obviously know the input u. Can we now use those two signals to try to create a model that will estimate the dynamic behavior of our system so that we can now find an x hat that's trying to replicate or estimate x? We're trying to build an estimator. A full order estimator means we're trying to estimate every one of these 10 components in our state vector x, which we're going to call x hat. And how are we going to do that? Well, we're going to pull out the copy machine and just copy what we've already created. So we had up top, we have this original system. Down below, we've just copied that same representation. If we think we know the system, then we think we know the system matrix phi, the input matrix gamma, and the output matrix H. What we are doing is we are now comparing. And we're saying, oh, the true system, which is up above, is giving us an output y. Our estimate of that is giving us a y hat. Why are those different? It's the exact same thing. Bottom and top. Why would y hat be any different than y? It's not a trick question, but it's kind of a interesting question if you really haven't thought about it that much. We are now trying to estimate the state vector. Do we know where we originally start with our state vector? Do we know the initial conditions on x? Maybe not. Maybe we don't know how to initialize x hat. Maybe x starts with a position and a velocity, and we don't know what those are. So we don't know what x hat is going to be. Maybe we initialize those to 0. Well, then y hat is definitely not the same as y. So we compare y hat with y. That's going to give us an error, and we use that error to now adjust the estimate or the dynamics of x hat of L plus 1. And that L sub p is similar to what k was in our full state feedback approach, except now we call that L sub p our estimator gain, not the full state feedback gain. L sub p now tells us how fast, or the selection of LP tells us how fast we want the estimator to be in estimating or forcing x hat to approach x. There's a lot of information here tonight, but you know, you guys are well fed, have your snacks. So here's a little piece of information. L sub p, you want to select that so that the dynamics of your estimator are fast enough to give you a good estimate of x hat somewhat quickly. Or I'm sorry, make x hat a good estimate of x somewhat quickly. So if you want your closed loop dynamics to have poles, let's just throw some numbers out here, at 0.8 and 0.9, you might want your x hat to get to x much faster than x is going to get to its final value. So you may want to think of your x hat dynamics in a smaller circle than what your closed loop dynamics are for x. So you might want your estimator to be a factor of 2 or 5 faster than your closed loop dynamics, and that's what's going to influence your selection of L sub p. And that's our goal. We want x hat to approach x as the time index increases, and that means we need to select this estimator gain L sub p, and this is how L sub p enters into our estimator dynamics. Our system matrix phi, our output matrix H, and L sub p now shapes how the output is directed into our system dynamics through L sub p. And we can now, as you go further on into control, you would say, oh, this looks like a dual problem. If you transposed that equation, you would have phi transpose minus H transpose L sub p transpose. And now L sub p transpose looks like the K in our phi minus gamma K. Just saying. I'm sure you're going to remember this 10 years out when you start designing full order estimators, and you're going to know all of this about duality and dual problems, etc. But if you have an algorithm, which you do in MATLAB, it's the place function, P-L-A-C-E. You can use that to design L sub p. You can use it to design K. Now, If that estimator is effective, why don't we use it, x hat, to actually control our system? Because now we're assuming we can't go in and access x. Our system dynamics don't allow us to have that many sensors, let's say. We've now created an estimate of x, calling it x hat. Well, let's just use x hat as if it was x and feed that back through this full state feedback gain matrix K that you better know how to design on the final. You don't need to do this, but you need to be able to design a K, assuming we could go in and access x. We're throwing that away and saying, let's get real, let's get more practical. Now all we can measure is u and y, and with those, you can now build up this bottom half of the diagram in a computer, and that computer now is turning out estimates of the actual state. You're using those to control the system. And that's what our goal is here. We want to estimate x with x hat and control the system with x hat, meaning u is now minus k x hat. Question?
So, I guess the idea is you're trying to come up with an estimation of your state and use that to actually drive the system, right? How much faster does your observer or estimator need to be able to actually give just set up enough time to drive the error to zero?
The question was, how do we select, I think, in a nutshell, how do we select L sub p? How do we select our estimator gain to make our observer? You're going to hear this many different ways. You'll hear it called an estimator, an observer. How do you select the speed of that estimator if you're putting all of this together and you want your closed loop dynamics to be influenced by phi minus gamma k, the K matrix? It really is problem specific. I can't tell you make it a factor of 5 faster. I can't say make it a factor of 10 faster. If you start pushing things too hard, too fast, it may drive x hat too rapidly out of what x needs to be, and that may make your closed loop behavior worse. So there's a trade-off between how fast you make your estimator versus the performance of your closed loop system. So I can't really tell you, oh, make it a factor of 2. Oh, make it a factor of 5. Oh, make it a factor of 10. You'll have to essentially look at your system that you're playing with and say, what can I tolerate or what can I push my system in terms of performance or behavior based on my estimator dynamics or observer dynamics and the full state feedback dynamics. So I can't give you a definitive answer to that question. Yes?
So is x hat an estimate of all the states in x, or is it just the ones that cannot be measured?
So the question was, is x hat an estimate of all the components in x, or is it just the ones that can't be measured? So the wording here is critical. I said a full order estimator, so that means I'm estimating everything in x, but you'll find in the literature reduced order estimators or reduced order observers. That then just says, you know what, I already have x sub 1 and x sub 4 and x sub 7. I don't need to estimate those. I can measure those. Let me just measure or estimate the ones I can't measure, and that's now a reduced order estimator. That's a little bit more, I guess you've already followed all of this, so maybe I should just keep going with reduced order. So this is the more direct way of explaining, but if you want to go further, the next process might be, oh, let's build a reduced order estimator. In this case, how big is your estimator? Now you've built a 10th order estimator. If you do a reduced order, maybe you only have to estimate 6. So you don't have to have as much computational machinery happening if you do a reduced order estimator. But now you're assuming that your measured variables are accurate and you don't have to use a Kalman filter or anything to try to clean up the noise in your measured signals. A lot of trade-offs that we haven't had the pleasure to experience in this class. But those are valid questions. But in this case, what I've given you so far, phi is exactly the same phi as our full dimensional system. And so it's a full order estimator, and so this is called a full order controller or full order compensator. Your compensator now will be 10th order. And you thought the PID was complicated. That's second order. Come on. So now if you had a 10th order system and you did a full order compensator, you would be automatically using a 10th order controller. Let's now look at trying to come up with this augmented set of dynamics from our desire to build an integral control strategy. We have the block diagram. We know how to build an integrator. If I told you, give me an integrator on the final, you better be able to just draw me that 1 over z minus 1 block and say, oh, you inject a waveform into that and it's going to produce at the output the integral of that. That's now just a numerical way to integrate. Well, we've now put that into our system. We've augmented our system. The original system is this system in black that has gamma, phi, and h, and z to the minus 1 is a bank of delays. We're assuming now, again, that we have access to the full state. We're just trying to show this concept. What we want to do is try to figure out how can I extend or augment my original dynamics so that I can model this and build an extended state feedback vector that includes the k sub I. Meaning, in order to implement this block diagram, we need to find k sub I and k hat. That's what we want to do now. So, let's look at the dynamics of the integral piece. There's our integrator. And what we're assuming is we're taking some waveform, and in our particular case, that's the air signal, E, and we're producing a new component of our augmented state, which we're calling x sub I. And in fact, this process is sort of a review for the final. If I now gave you that and said, oh, build a difference equation from this. Obviously, hopefully the transfer function will be a little bit more complicated than that on the final. Need to make sure you know your stuff. So now I give you a block diagram and I say, give me the difference equation. Well, you would now say, oh, I can find in the frequency domain, x sub I of z is just the output of 1 over z minus 1 times E of z. If I cross multiply, in the frequency domain, I have this relationship between my new vector component, x sub I, and the air signal E. What happens when I take, well, let me just do one more, let me distribute x sub I and we should be able to take that into the time domain. What's z times x sub I in the time domain? That's now just advancing the time domain variable of little x sub I by 1. Or we now have little x sub I of, let's say, L plus 1. And that's equal to x sub I of L plus E of L. We okay with that? That was pretty straightforward. Now what we want to do is really just remember what we were calling this air signal E. E was in fact the output Y of L minus the reference input R of L. But Y of L we can relate to our original state vector. That's just the output matrix H times X minus R of L. What I want to do now is simply put this in there so that I have my dynamics of my integrator in terms of that state variable, x sub I, the original state x, and the reference input R. I don't want to have y included in that, and now I've eliminated y by rewriting y as hx. Now I can rewrite my dynamical relationship of my integrator state. That's now x sub I at L plus 1 equaling x sub I of L. And that makes sense. If this is an integrator, we're just remembering what we had in the previous step, and we're just adding to that. And what we are adding to that now is plus hx of L minus R of L. Where that is just our E of L, and this is now what I would call the integral dynamics. Meaning, we now have a difference equation, and it's dynamic for the additional state variable that we've introduced, which is x sub I. We want to now add that on to our original system dynamics, and I'm going to say that that's now going to be what we will augment the integral dynamics onto the original dynamics. Or what am I saying? I now say I'm saying x sub I of L plus 1 is equal to x sub I of L plus h x of L minus R of L, and I'm using that together with my original system dynamics. X at time L plus 1 is phi x of L plus gamma U of L. And what I want to do, and now I'm actually doing it in the opposite stacking arrangement than what I was talking about before. I think before I said augment x sub I on the bottom. Now I'm putting it on the top. But now I'm saying build up this 11-dimensional vector. I'm assuming now x was 10th order. So x had 10 components. X sub I has 1. I'm putting that additional one on top of what we started with. That now needs to be in the notation of a state space representation. That now needs to be some matrix times my state vector at the present time. And what's in that state vector? or how big is this? How tall is x sub I? How many components did I have in x sub I? X sub I said I had one input, so that was the 1. And how tall is little x? That's now n, isn't it? It's Nevada tall. If that's the case, I'm now going to compatibly dimension, or basically break up this augmented system matrix into 4 parts. I want to now fill in those parts based on this dynamic information up above. I need x sub I of L plus 1. Let's work on the top one first. And in fact, I'm going to need something times u plus something times r to include all of the pieces that I need. How do I fill in those? How do I fill in the top row? Or the top compartment? I want really x sub I of L plus 1 is the very top black line that I've written. I want x sub I of L to be included. How do I pull that in to the right-hand side? Do you see that I just put a 1 right there, and that will pull off the x sub I, and now I need hx of L, so here's my output matrix, H. Do I have any u in the top row or in the top dynamic equation? No, but I do have an r, and that's now minus 1. What's in the bottom row? Do I have any x sub I explicitly impacting the dynamics of x at time L plus 1? No, so a big 0 goes there. And what goes in the 2-2 submatrix in this augmented system matrix? That's now our phi. Here's a gamma, and there's a 0. So if we wanted to call this, we could say, oh, here's our augmented system matrix, phi bar. Here's our augmented input matrix, gamma bar, and you can find the dimensions of those. Phi bar is 11 by 11. This is now 1 by 1. This is n by 1, so that 0 is in fact a column of zeros. It's a column that's n components tall. H is 1 by n. We had one output, and phi is n by n. So this phi bar is n plus 1 by n plus 1. And the gamma bar has n plus 1 rows and 1 column, and the matrix that is multiplying the reference input is now 1 column wide and 11 rows tall. Do you see how we could now find the k sub I and the k hat? That is going to now be determined by the K matrix associated with this full state feedback design problem involving phi bar and gamma bar. So the control law from the block diagram was u of L is equal to minus k hat x of L minus k sub I x sub I of L. Oh, and maybe I should have, let me change that to be in the order that I did it now. It's now k sub I x sub I of L minus k hat x of L. Or this is now minus k sub I partition k hat x sub I of L x of L. And you could think of this as an augmented full state feedback gain matrix. And it's just been added to by one additional component, which is the k sub I. But if you can now find the k bar, you can partition this. This is now, let's say it's single input, that's 1, this is 1, and this is n. So now it's a 1 by n plus 1 row vector. That's k bar. And that's what you could use up here to control your integral controlled system. You'd now plug in the k hat where it belongs and the k sub I where it belongs, and that's now how you could control your system. Let's get ready to rumble. Let's get back into something that maybe you can connect with the final. Suppose I gave you the following. Suppose now maybe I shouldn't preface it this way, but maybe the final exam will be challenging. And I gave you a present, didn't I? I gave you a practice final exam. If you haven't looked, there's now a final exam that you can look at to get a feel for what's going to happen a week from Thursday on the final exam. So let's look now. Suppose you are given a challenging system to control. And suppose that challenging system, or why am I even calling it challenging? Suppose it's now 2 times a factor z minus 3 over 2. And downstairs we have z minus 1 and z minus 2. And I want you to stabilize that system. Do you see that it needs to be stabilized? The first thing you might be doing is thinking, okay, let me just look at what's happening to this system. I have a pole at 1 and a pole at 2 and a 0 right between those. What happens if I now applied output feedback? And maybe that would be the question. I might say, what can you do, or what happens to this system when you apply output feedback? And now what would be one way to answer that question? If I said, what's possible from this system when it's controlled with output feedback? What am I trying to, or what's one possible way that you could be thinking of answering that? Really? Eyes on teacher. Everybody's looking down, trying not to make eye contact. I don't want to answer. But what am I asking? Draw the root locus. So now, what's the root locus of this look like? Now I'm to my bread. Don't have much longer. Good. So, what do I have? What's my root locus for this? How many branches of the root locus do I have? 2. Why do I have 2? Because I have 2 x's. This right now, I haven't put any controller in, but if I had introduced poles and zeros from a controller, then I might have more branches of my root locus, because I'm sketching G and C in my root locus. Here I'm just saying what happens with output feedback. Output feedback, I'm not putting any more dynamics in, I'm just using a gain in my closed loop. In this case, I have two branches of my root locus. Are any of the real line segments, do any of those belong to the root locus? So now I've cut up my bread. I have my plastic knife, since this is a non-weapon campus, and I've sliced my bread at 1, 1.5, and 2. I'll take the piece from 2 to infinity. But is that on the root locus? No. The only pieces on the root locus are those. Where do I have any branches off the real axis? How many branches are going to infinity? 1. How many? What's my pole zero excess? 1. So my pole zero excess tells me how many branches are going off to infinity. And I just have one branch going off to infinity, and it's zipping off to minus infinity. Can we stabilize this system with output feedback? So now if I ask you what can be done with output feedback, and you just sketch the root locus and you don't annotate it very clearly, you might not get very many points on the final. So now what would you say in your summary paragraph on the question that says what can be done with output feedback in this system? How long is your summary paragraph going to be? Doesn't have to be very long, does it? 1 or 2 sentences. This system is not controllable with output feedback, period. One of the branches of the root locus always remains outside the unit circle, period. Done. Move on to question 2. Right? Is everybody clear on that? All right, now I say, well, that was part A, and we have K parts to this problem. Okay? So now I say, can we stabilize this system with a controller? Can you design a controller to stabilize this system? There's our system, and those x's are supposed to be on the real line. Now what do? We pull out our food theme again. We pull out our shakers, pole shaker and zero shaker. Not much nutrition in those, but we can sprinkle poles and zeros onto the z-plane. Where do we sprinkle them to stabilize this system? What are we trying to do? We are trying to get somehow away from being stuck between 1.5 and 2 in the z-plane. How do we become unstuck between 1.5 and 2? What are some of the strategies? Does somebody have a design already? Place a pole on 3.5. How many points do you want on the final? You just lost 200 out of 100. Right? What are we never, ever, ever supposed to do? We can't cancel pole. It's very tempting, isn't it? Because we want to get rid of that character. But this still wouldn't solve, this wouldn't solve our problem, would it? So one it would cost you dearly. So let's not do this, because we never ever, that's why we talked about Ragazzini for so long. Boy, Ragazzini, that sounds foodie or something. But anyway, Ragazzini told us constraints. And what were those constraints? Those constraints said, constraint 2, don't cancel open loop zero factors or zeros outside the unit circle. And the other one was don't cancel poles in this, we can't cancel unstable poles with unstable zeros. That was rule number 3, really. That's why we had those constraints. So we don't want to be doing this or this, because those two are outside the unit circle. So we can't do that. But what did we learn how to do? Do you remember? Well, now you might say, well, I don't know, I can't remember. So what do you do? Well, you maybe modify the problem. You say, well, I don't know how to do it, Dr. Tharp, but suppose that zero and the pole weren't there. I can control this one. Good. At least you're showing me that you're evolving towards a solution, right? You're starting to show me that at least you don't just leave it blank. Pull out a napkin and give me the napkin when you leave. It may have tears, it may be damp, but I'll take it. There's maybe a garbage. No, there is no garbage can in here. But anyway, you could stabilize this one, correct? This one you can stabilize with constant output feedback. You have to crank up the gain enough to get you into the unit circle and not too much to get you out. Okay, but that's not my problem, Dr. Tharp. You gave me this one. So how do we do it? Well, do you remember if the zero was sitting maybe here, how we controlled that one? Now we're in our restaurant again, aren't we? Two poles walk into a restaurant with a zero on their left. Remember? So now our controller would say, oh, I can put that there, and these two are going to be coming together. How many branches now do I have of my root locus? How many branches I have 2 because I have 2 poles. 2 are on that same segment between 1 and 2. Between the 2 poles, there's 2 branches. They will now meet and what? Break away. So now we have a breakaway, and then they will re-enter. One will go to the finite 0, and we'll have one branch going off to infinity. And that will be a circle, with the radius being the geometric mean, with the center being at the 0. Oh, can we use that information to help us here? We know we can't put it here, right? But boy, we sure are wanting to, but what if we just put it right here? We can put it outside the unit circle, we just can't cancel with it. Now what happens? Are we better? Don't go counting your chickens before they're hatched. What do we have now? We have this piece. We have this piece. How many branches do we have? How many root locus branches do we have? How many poles do we have? 3. So now we have 3 branches. We have 2 between that red pole and the pole at 2. They will come together and break away, and we have another branch between 1 and the 0. Okay. Is our root locus done? No. What happens? What's our pole zero excess? We have 3 poles, 1 0. We have 2 more poles than we have zeros. We have 2 branches of our root locus going off to infinity. And where do those branches go? 180 divided by 2 at 90 degrees. So they go off at plus and minus 90 degrees. And you could calculate the centroid if you wanted to. But we would just say, oh, it does something like this maybe. This guy goes here, and one of these goes up, and one of them goes down. Do we stabilize our system? No. All right. What else can we do? Well, we just keep drawing. And we just keep drawing. The exam's 2 hours, the final. Just saying. Well, it kind of got us started, didn't it? Sort of. What happened when we did the following? What happened when I gave you this? I hope I can give you the right example. What happened when we had, let's say this one was at 1 and we had a 0 out here. Do you remember what we did with this one? Did we do this? No. No, we didn't do that. What did we do? Here we're stuck, aren't we? There. So we don't want that. I shouldn't have drawn that. That's going to be hard to erase. But let's see if I can. Doesn't take much to amuse me. But what did we do here? Didn't we put a 0 there? And now a pole here? We can't just put a 0 down, can we? It has to be matched with at least 1 pole and maybe more. But now we've got this one fixed, don't we? How many branches of the root locus do we have here? 2. And what are we doing? We're starting here, and these 2 are breaking away, and they're re-entering there. And how many branches do we have going off to infinity? 0. We have a pole zero excess of 0. But as long as we don't crank up the gain too much, we can be inside the unit circle. Wow, that works. Okay. What happens now? Can we combine those 2 thoughts? We had a pole here, and a 0 there. And you just said, oh, put a pole there and a 0 there. Now what happens? Looks like we've got eyes looking at me. Ooh. Is it going to work? Well, sketch. Don't just shrug your shoulders. Let's look. So we have a piece there. We have a piece there. And do we have any more? We have how many singularities? 1, 2, 3, 4. So we have something going off here, don't we? Is that going to work? No, probably not, because these 2 break away and enter here. And those are still outside the unit circle. What can we do? Well, I'm going through this activity to maybe convince you that sometimes just trial and error starts becoming futile. And so maybe what you want to do is say, you know what? Tharp told us how to design a full order compensator, and as long as my system's controllable, I can at least build one of those and see what happens. And that might inform my design of something to control this difficult or challenging problem. So now, as long as it's controllable, our system. Do we know if this system is controllable? Where is this system? Here it is. How would we find that? Can you now? So here's a question. Boy, I want to stay. Can you now, here's a problem for the final. Can you create a state space representation from that G of Z? Yes, you better be able to, and then you could check controllability. And because we don't have any poles and zeros canceling, this is controllable. So, it is a controllable system, and what I did today, before class, sometime, I said, man, how am I going to figure out how to sprinkle poles and zeros? So I said, let me design a full order estimator. And you know what happened? Here's what happened. It gave me a 0 right there, almost canceling, but not quite. It didn't. And what else did it give me? I'm going to have to look at my notes. Can I cheat? I hope I wrote it down. Okay, it gave me another pole over here at almost 2.5, and it gave me another pole way over here at minus 3.73. Can we sketch the root locus for that? Oh my, look at what time it is. I'm sorry. I apologize. This may be your last class ever, so if we go a few minutes over, you can just celebrate, right? So what happens here is we have this section, and that, I'm running out of speech. And what else do we have? 1, 2, 3, 4, 5. We have this guy. And what's going to happen? Well, this one's kind of a challenge. Eventually, these come and they go there. These two come over here. And these, so we have one going there and one going there, and this one comes in here, and eventually it meets up with that one and goes off like this. Didn't you see that one coming? So actually we have 4 branches simultaneously inside the unit circle, and it is stabilized, but it ended up being we had to put a controller pole at 2.5, another controller pole way over here at minus 3.7, both of those outside the unit circle, 2 unstable controller poles, and we put a controller 0 outside the unit circle, but voila, we adjust the gain just right, and we can end up inside the unit circle. Just saying, you may need to resort to some additional tools, which you now have in your toolkit, full state feedback estimators, to inform your decision on how to design or sprinkle poles and zeros onto your Z-plane. We'll pick up, oh, this is sad. So tomorrow we have a review session if you want to. It's at 4:30 in Harville 204, and I'll see you there, or definitely I'll see you at the final here a week from Thursday. Good luck on your final exams.